Welcome to this lecture series in real analysis. In this lecture, we'll define the notion of dense subsets of R and show that the set of rationals is dense in R. And let us recall what we need. So we need to know this fact that the infimum of the reciprocals of all the naturals is 0. Or you can forget about the previous one and remember just the Archimedean property, which says that whenever x is a positive real and y is any arbitrary real, then there is a natural number n such that n times x exceeds y. So they are more or less equivalent. One can prove one from the other, but at any rate, it's good to know both of them. All right. So here are some problems for practice. And now let us get started. So first we will define what is called an open interval. So a subset I of R is called an open interval if there exist real numbers a and b such that I is of this form. And as a point of notation, this can also be denoted as that. So a subset I is called an open interval if it is the set of all the points between two given real numbers, strictly between. So in this picture, all the things that lie between a and b constitute an open interval. Now, having defined open intervals this way, sometimes, or in fact many authors and even myself at many points might consider things like these also as open intervals. So what are these? These are all the real numbers which are strictly less than b. So this might also be considered as an open interval. The definition would need to be, one has to make maybe 3 bullet points to accommodate them, but let's not worry about those things. So this is the definition of an open interval. It's a very simple definition, and let us proceed. So now we define the main concept of this lecture. A subset A of R is called or is said to be dense in R if for each open interval. So just give me 1 second. Here I forgot to say A less than B. So here I wanted to say A less than B. Otherwise, this set would be empty. And we do not want to regard the empty set as an open interval. Okay? Fine. So a subset A of R is said to be dense in R if for each open interval I of R we have that the intersection of I with A is non-empty. So in other words, every open interval contains some point of A. Every open interval intersects A non-trivially is what this is saying. So in some sense, this is present everywhere. No part of the real numbers can escape the set A, right? That's what it is trying to capture. So let's foster our understanding via some examples or non-examples. So here is our very simple non-example. The set of integers is not dense in R. So here we have drawn the set of integers. And to show that this is not dense in R, we must exhibit an open interval which does not intersect integers. But such an open interval is very easy to find. For example, one can just say restrict your attention to this much, which one may say is just 1/3, 2/3. 1/3 and 2/3. So if you take I as this open interval, all the things between 1/3 and 2/3, then I does not intersect Z, and therefore Z is not dense in R. And in fact, one can find many such open intervals. Alright, so it's a very simple example. And note that if we have a dense set, once we find a dense set, then every superset of it is also going to be dense. If every if every open interval intersects A, then every open interval will intersect any superset of A, trivially. So that's that. But now for the interesting part, the set of rationals is dense in reals. This should be pictorially clear because if you kind of visualize the rational numbers, they are sort of everywhere. As we saw, there are real numbers which are not rational, for example, square root of 2, but still, they are present densely in reals. So we want to show that every open interval intersects the set of rationals. Every open interval contains at least one rational number, is what we want to show. So let's do it. So let I be this open interval, A comma B, where we assume A less than B, of course. A and B are some arbitrary real numbers. Now we will give the proof under the assumption. We will assume that A is greater than 0. Or maybe I will write it this way. We will assume this, but of course this is not necessary. So the case where A might be less than 0 and B might be less than 0, or all the other cases, they are left as an exercise. We will just exhibit the proof in this particular case, just so that our exposition is clear. No new difficulty will arise in those other cases where A may be negative, etc. Okay, so this picture is what the situation right now looks like. We have a positive real number A, something greater than A, and we want to show that there is some rational number inside this region. Alright, now by the Archimedean property, we can find n such that n is a natural number, such that 1 by n is less than b minus a, and 1 by n is also less than a. Now, why are we even considering such a natural number? First, let me explain that. So here is the idea. How are we going to show that there is a rational inside this interval? Our idea is pick n so large such that the reciprocal of n is very close to 0. So this is 1 by n, where little n is very large. And then if you keep walking with this step, so this is 1 by n, this is 2 by n, this is 3 by n, then 4 by n. If you keep walking with that small step, at some point you are bound to fall inside this pit. So if your step size is very small, so small that it is even smaller than the pit width, then at some point you should fall inside the pit. But of course, your step size should also be smaller than the starting point of the pit. So step size is smaller than the starting point, step size is smaller than the width. Okay, so that's why we are considering such natural number. And now why does Archimedean property imply that such a natural number exists? So first, let's just concentrate on this part. All we are saying is that there is a natural number n such that n times b minus a exceeds 1. And this happens due to Archimedean property, because just think of this as some arbitrary real, and this is some positive real. So such an n exists. And here the same thing. This is some arbitrary positive real, and this is some arbitrary real. So 1 is less than na for some a. And now you just choose the bigger n of both. Whichever n worked here and whichever n worked here, just take the bigger one amongst the two. That will work for both. So just make sure that you follow this point. Or if you don't like to use Archimedean property, you can just immediately prove this by using the fact that infimum of this set is 0. So by using this fact also, you can show the existence of such an n. Okay, so far so good. So now, once we have chosen that n, let me mark it here. So this is 1 by n. And now the point is, the proof basically will go as follows. You keep walking up until the point you are just before the starting of the pit. This is the pit. So you are just before the starting of the pit. What does that mean? It means that in the next jump you will cross the starting of the pit. All right. So let k naught be the maximum of all those natural numbers such that k by n does not exceed a. Right? So what are we saying? We are saying k naught is the maximum number of steps you can take before you cross the entry or the starting of the pit. So before we even say, take the maximum, note that this set is bounded. Why is it bounded? Because of the Archimedean property. We have a fixed natural number n, so this is some real number which is positive, and therefore if you scale it by natural numbers, at some point you will cross any arbitrary given real, namely a. So for each large enough k, this happens, and therefore this is a finite set. Right? At the same time, this is a non-empty set because 1 lies in this set. 1 by n is less than a. So this is a non-empty finite set is all I'm saying. And therefore one can take its maximum, and its maximum is a is a natural number which we are calling k naught. So conceptually, k naught is the greatest number of steps you can take, where each step size is 1 by n, so that you have still not crossed a. All right. Fine. So now, so this immediately gives, therefore, k naught plus 1 by n must exceed a. Right? Because k naught is the maximum number of steps that you can take before crossing a. So if you take more than those steps, you will cross a. So we have that immediately. And now, but since this is less than a, we have, this is not less than a, this is less than equal to a. Less than equal to a, we have k naught by n plus 1 by n is strictly less than a plus b minus a. So what happened? This was less than equal to a, but this was strictly less than b minus a. Note this one. Right? 1 by n is strictly less than b minus a, and this is less than equal to a. So we have a strict inequality here. But what is the left-hand side of this? The left-hand side is k naught plus 1 by n, and the right-hand side is b. Okay. Combining this and that, we get, and we have located a rational number within this region, within the interval a and b, a comma b. So once again, the idea was you choose n large enough so that this is a very small number. And if you keep taking those step sizes, at some point you are bound to fall inside the pit. And when you fall inside the pit, you get a rational number, and that's it. You get a rational number because you are just multiplying 1 by n with an integer, with a natural number, in fact. So that's the proof in this particular case, and you can make other cases and prove this entirely, completely. And this proves the density of Q in R. With that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.